Okay. Hello, friends, family, and random internet strangers, and welcome to week 8 of Let's Read Code. So, this week, chapters 18 and 19, we're sort of shifting out of the technical details and getting back more into the history side of things and how we got to uh, computers as we know them today. So, the focus of chapter 18 is really more on like not necessarily the things that led to computers, but the various and sundry mechanical and electromechanical doohickeys that people used to count things or do math before computers really started being a thing. So, first thing we talk about is, abacus, which people seem to think started out with like rocks on other rocks that are able to slide around in about 300 BC. Um, I hope you've all seen these before. You move the beads around to count things, right? So very simple, but fairly effective mechanism for counting and being able to quickly add and subtract things. Much more complicated early counting mechanism, this thing that we're calling the Ankythera mechanism because of where we found it in this shipwreck off of this tiny Greek island. We think it comes from about 200 BC. We just basically have pieces of it. We don't have the entire thing put together, but the thought is this was a big mechanical calendar basically used to predict like moon phases and eclipses and stuff like that for various and sundry Greek religious celebrations and stuff. Book talks a little bit about Napier's bones from 1617. What's his name? Napier, first name. Napier. Where'd it go? John Napier. There we go. Scottish mathematician, came up with a lot of very, important mathy things. One of the big things was this Napier's bones thing, which really enabled you to multiply and divide and even do a little bit of logarithmic magic very quickly. Basically by, in this case, flipping over or rotating these sticks. Basically an automated multiplication table. Slide rules came along not too far after that and stuck around really for a very, very long time until about the 1960s or 70s when general purpose computers really started taking over. These things could pretty much do everything mathy from addition and subtraction and multiplying and dividing and trigonometry and logarithms and roots and all sorts of other things that made them incredibly handy for doing math very quickly. 1642, Blaise Pascal invented the Pascaline, which was the first, not necessarily the first, but the first commercially successful, commercially available automated mechanical adding machine. The big thing that made this successful, just like we talked about a couple of weeks ago with how we implemented carrying when we're doing addition, this was the first thing that really handled that mechanically in an automated fashion. So specially designed gears inside actually carry when a lower digit carries over, it actually hits something in the next digit and makes it go up by one, which was kind of a big deal at the time. One of Pascal's contemporaries invented the stepped reckoner. Very similar thing, not nearly as successful because it didn't work quite as well. But core concept was very similar, just a big bunch of gears that added and subtracted stuff. 1804 brought the Jacquard loom. Pretty cool piece of machinery. Basically lets you weave really complicated patterns into cloth, not by hand, but by punching holes in little paper cards that got fed into the machine. this big continuous roller thing, and the machine would figure out where the holes were in the cards and weave that pattern into the cloth. So let you make very beautiful, big, complicated tapestry things without, having to do a whole lot of work. Early 1820s, we get to Charles Babbage, who was one of basically the fathers of modern computing in a lot of ways, sort of set up not necessarily the hardware, but the theoretical bits of how computers work that we can really still see today. So his first machine started in about 1820, finished in about 1822, was the difference engine. Basically, this thing was made to calculate logarithm tables. So this is back in the day where if you wanted to do logarithms of things, you generally didn't actually sit and figure it out. You would go look it up in a table that someone else put together, because it was very complicated to actually sit and do those calculations without, computers and stuff. So the point of the difference engine was basically to automate that whole process of calculating all of these logarithms and spitting them out in a way that you could basically go feed into a printing press and automatically print those tables for people. So he made a small scale version that actually worked, got funding from the government to go make a much larger, more practical version, but never actually finished the bigger version. He kind of ran out of money and got distracted by another project, and the government got all unhappy and cut off more funding for him. The project he got distracted by was even less of a success than the difference engine, but really laid a lot of the groundwork for what computers are today. This thing was called the analytical engine. Instead of just calculating, differences over and over and over again, it was a little more general purpose. You could feed in instructions on punch cards, just like the automatic weaving loom, and it would carry out those instructions. Again, asked for government funding for this to actually build one. Between the fact that this was really expensive and machining capabilities at the time weren't quite up to snuff for what he actually needed to build this thing, it never actually got built. People have made replicas. There's one basically complete version built in some museum over in England that, actually does work, but it never got built in his time. But the core concepts of how he designed the system are basically the same as how modern computers are structured, right? So we talked last week about, and the week before, about how computers are the technical definition of a computer. You have some sort of input, you have storage, you have processing, you have output, right? So this machine was basically built around that concept. It had a store, which I think this is actually a picture of the store component, where it would store data that it's working on. Concept, or the component that he called the mill, which actually did the computation-y bits, and then had input via the punch cards or via mechanical switches and stuff to feed in instructions and data, and then output typically in the form of like either punch cards or some sort of automated printing doohickey. Along with that, we get Lady Ada Byron, the Countess of Lovelace. So she was at one point commonly acknowledged as the first programmer, effectively. Later research has kind of cast some doubt onto that so much, but she did really produce one core concept to go along with Babbage's analytical engine that has had very far-lasting impacts into how computing has developed. So a quote from a biographer: Ada saw something in Babbage that in some sense he failed to see. In Babbage's world, his engines were bound by number. What Lovelace saw was that number could represent entities other than quantity. So once you had a machine for manipulating numbers, if those numbers represented other things like letters or musical notes, then the machine could manipulate symbols of which number was one instance according to rules. So she was the one who really kind of came up with this idea of, at least in a practical sense, here's a computer, it works on numbers, but just because it's working on numbers doesn't mean we can't use those numbers to represent other things and do useful computation on stuff that's not just strictly adding numbers together, right? So next big thing comes in 1880s, 1890s. A guy named Herman Hollerith was hired by the United States government to help process data for the United States Census. So the 1880 census and all of the data that it took, that it collected, going around asking everybody in the country about who they are and where they live, it took like 12 years to get through all of that data, which is bad because the census happens every 10 years. So by the time they got finished doing all the data crunching, it was all bad because it was time for the next census to happen, right? So taking the whole punched card concept, instead of the census workers going around and writing down a bunch of stuff, they would punch holes in cards, which would then get fed into one of these tabulating machines. And thanks to some spring-loaded pins and pools of mercury and relays and other electromechanical goodies, it would actually count how many times it saw a card with a certain hole punched, right? And through that, the census data, which in this case had about doubled the amount of data they collected, and they finished all the results and got actual useful data out of it in, you know, like 2 years instead of 12, which is a very good thing. And then the company that he started to do this bought out a couple of other companies and eventually turned into IBM, which, you know, still one of the big players in high-tech supercomputing kind of stuff, as well as establishing the personal computer back in the 70s and 80s. I'm going to jump ahead to the 1940s now and look at what is commonly recognized as one of the first large-scale electromechanical computers, or at least the first one in the United States. There were a couple other smaller things happening in other countries, but this is the first really big one. Harvard Mark I, built in, or finished in 1943. This one, really cool thing about this one, this was the first thing that actually had a printer hooked up to it and could actually like print numbers as results instead of just dots or punch cards or things like that. It was followed up shortly by the Harvard Mark II, which was entirely relay based. So Mark I had some other mechanical bits in it. The Mark II was entirely driven by relays, right? So this puppy was used at Harvard to teach some of the first computer science classes in the United States, or in the world, I believe. While all that development was going on, over in England, to help support the war effort in World War II in decrypting secret German communications, started with the bomb, which is, again, a mostly mechanical, slightly electromechanical computer that was used to help automate the process of trying to decrypt encrypted German communications. It was followed up shortly after in 1943 by the Colossus, which was, again, I believe this one was entirely or almost entirely relay based, and again really sped up the process of being able to quickly decrypt German messages so that we knew what was going on. All right, one more and then we'll flip over and watch some rocket launchy stuff. Rewind back in time a little bit to 1904. This is when vacuum tubes got developed. So relays are cool and all, but they are slow. Like they physically take time for the little lever inside to move back and forth, right? So vacuum tubes are basically light bulbs with a few extra special things going on inside of them that can perform basically the same job as a relay. So when you feed in power to one side, it can basically turn on another connection, right? They move a lot faster than relays do, but the slight downside is, again, because they are light bulbs, they do burn out eventually and need replaced fairly often. One of the first computers built mostly with vacuum tubes was ENIAC in Pennsylvania, used mostly to compute things like missile trajectories and stuff like that. So again, that was 1946. Its successor, UNIVAC, was the first like commercially successful computer. Like it actually got sold to other corporations and companies and stuff. So that was kind of a big deal. Its big claim to fame was doing data processing and crunching to handle predicting some results of a presidential election in the 50s. So that was a pretty cool thing. Really brought computing to the forefront of sort of popular culture, if you will. Okay. Our rocket is about 1.5 minutes from launching. So we're going to go watch that for a little bit.
Nine is in startup. Eight is in countdown. FTS is armed for launch.
After a minute now, the FTS, the flight station system, has been armed.
Dragon, SpaceX, go for launch.
SpaceX Dragon, we're go for launch. Let's light this candle.
T-minus 30 seconds.
Stage 1 tanks pressing for flight.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Falcon 9, Dragon, gate and 5 speed, bottom dive.
America has launched. So rises a new era of American space flight, and with it the ambitions of a new generation continuing the dream. 20 seconds into flight, stage 1 propulsion is nominal.
Plus 30 seconds into this historic mission. Flying crew on board Dragon and Falcon 9, and look at them go.
Falcon power telemetry nominal. M1D throttle down.
We're throttling down to get ready for the period of maximum dynamic pressure. We're in the throttle bucket. Reports say all systems are go.
Vehicle is supersonic.
We've exceeded Mach 1 on the Falcon 9.
M1D throttle up.
We're throttling back up to full power as we're through max Q.
Copy 1 Bravo.
And we heard that 1 Bravo call out that this is the second abort zone that they're in. They'll continue to be on this. So the first stage has done its job. They switch over to the second. At this point, Bob and Doug pulling about 2.3 Gs, 2.3 times the Earth's gravity, already moving at over 1,500 miles per hour.
We've heard the call out for MVAC engine chill. That's getting the MVAC engine ready to light. That'll come at about 2:44 into flight. Right now, everything continuing to look good. Next major event coming up is going to be the triple. We'll have main engine cutoff of the 9 first stage engines, stage separation, and then ignition of the second stage engine to continue to carry astronauts into orbit. Coming up in about 20 seconds.
M1D throttle down.
You heard we're throttling down the Merlin engines on the first stage. And we have MECO.
Eco.
Alpha. Falcon stage separation confirmed.
Copy 2 Alpha.
MVAC ignition.
All right, we have stage separation confirmed. The first stage beginning its flight back. Second stage being powered by that single Merlin 1D vacuum engine has ignited. Now carrying Bob to orbit. So they're going to continue under the power of this second
Stage
stage
2 propulsion is nominal.
off at SECO, or second engine cutoff, 8 minutes and 44 seconds into today's flight. So a little over 5 minutes to go still on this second stage. We heard the call out 2 Alpha, so they're now in the longest abort zone that carries them away from about North Carolina up the eastern seaboard, almost to Canada. Things looking good though, getting good call outs, nominal propulsion on that second stage. They're continuing to make their way into orbit.
Dragon SpaceX nominal trajectory.
Acquisition of signal, Bermuda.
SpaceX Dragon nominal trajectory.
Right here in nominal trajectories, the Dragon pointed in the right direction, continuing to make their flight uphill for an acquisition of signal Bermuda. That's one of the ground stations that are using to get telemetry and data back from this spacecraft.
Stage 2 propulsion is still nominal.
A little over 4 minutes, 40 seconds flight. Bob and Doug flying at 5,600 miles
Dragon
per hour.
SpaceX nominal trajectory.
Already almost 200 miles
Nominal
downrange
trajectory.
from the Space Center. Nominal trajectory continuing. While they can uphill, looks like we are getting a view of the first stage as well.
On your right screen, you can see that first stage with the grid fins deployed. It's making its way back to attempt to land on our drone ship, Of Course I Still Love You Today. We're just about a couple minutes away from the entry burn, and that's where 3 of the 9 Merlin engines do ignite to help slow the vehicle down as it re-enters back into the Earth's atmosphere. And then after the entry burn will be the landing burn, which is just a single
Dragon
engine burn.
SpaceX nominal trajectory.
And you heard
Nominal
Starting chill.
they are still on a nominal trajectory on Dragon, still on second stage, and that's that MVAC engine on second stage on your left screen. Again, on your right screen is that first stage booster coming back towards our drone ship, Of Course I Still Love You. We're about a minute away from entry burn.
While that second stage continuing to power Dragon orbit. You're keeping an eye on that timer. going to continue to burn until 8 minutes and 44 seconds into flight, a little over 2 minutes. Here, the call out Seco will then be a little.
Stage 2 propulsion is still good.
A little over 3 minutes. Dragon physically separates from the second stage of the Falcon 9. The upper stage gets a chance.
trajectory.
Dragon copy, nominal trajectory.
Continuing to check in with Bob and Doug. They are on a nominal trajectory. Just about 10 seconds away from that first stage. Starting that entry burn on your right screen, we should be able to see that view live.
Stage 1 entry burn.
And there is that entry burn beginning. This burn lasts about 36 seconds long.
Stage 2 FTS is saved.
That entry. We're just about a minute away from Seco. We'll have a number of events. Rapid session. Maybe the second engine.
Stage 1
We'll be
entry
looking for that stage 1 landing burn shortly after.
So just within a few seconds of each other. Such a cool view on your left screen, seeing Bob and Doug on Dragon. And now you can see the displays that they are seeing right now themselves.
And back to all stuff.
We are coming up 25 seconds or so away from Seco, or second engine cutoff.
Also the point where Bob and Doug are experiencing the highest G-force we're seeing encounter right about 1.8.
Copy Shannon.
For Shannon's final abort zone, if they were to abort at this point, be an abort to orbit or to land coast Ireland, standing by for
Stage 1 landing started.
confirmation.
And back to all step. And back shut down. Stage 1 landing.
Of Seco's second engine cutoff.
Now we are waiting for our first stage to make its way to our drone ship. Of course, I still love you.
SpaceX nominal orbital insertion.
Confirmation is nominal.
Dragon
orbital
copy,
insertion.
nominal orbital insertion.
What you're seeing on your screen is a live view of our drone ship, where our first stage will be coming down. Looks like we lost that live view, but we'll wait for confirmation of that landing shortly here.
Falcon 9 first stage is successfully landed.
And there you can see on your screen, Falcon 9 has landed. This is the first Falcon 9 to carry humans to orbit, so very exciting for us. And as you can see on your right screen, Bob and Doug are still making their way to their targeted orbit.
I want to recovery one.
So exciting today.
Doesn't stop.
It does not stop.
We did hear again good orbital insertions. That means Falcon 9 and Dragon right where they're supposed to be.
Penalty to FRC on recovery one.
Right at about 12 minutes when Dragon will separate. Looks like we saw a 0G indicator floating around there. Was a little bit about what exactly that is that they brought up with them.
And before separation, before Dragon initiates separation from the second stage, they do make sure to make, they do ensure that the vehicle is not spinning and it is in good condition before we separate.
Right, the upper stage does small attitude maneuver using old gas was built into the rocket body itself.
So we do expect that separation to occur in about a minute from now, but they do wait until they have full confirmation that it is ready to separate. Such cool views. I cannot get over this view that we're seeing right now. Bob and Doug on the big screen inside of Crew Dragon out in space.
Already 200 kilometers over planet Earth, a little over 124 miles, traveling 2,700 7,000 meters per second, 16,000 miles per hour. We're just standing by. That separation event should be coming up shortly. Begin a series of checks on the Draco thrust used to maneuver and power Dragon flight to the standing by for
Expected loss of signal or
sounds like we had an expected LOS loss signal on stations. Waiting for confirmation out.
Dragon separation confirmed.
Dragon separation.
There is a great view right in front of you. Dragon separating.
Separation confirmed.
And there's that call out. Dragon is now officially making its way to the International Space Station today.
Dragon SpaceX with that separation call. I'll have a few words for you from our Falcon 9.
Standing by.
Dragon, Chief Engineer on Dragon to Ground. Bob Doug, on behalf of the entire launch, thanks for flying the Falcon 9 today. We hope you enjoyed the ride and wish you a great mission.
Thanks, Bala. Congratulations to you and the F9 team for the first human ride for Falcon 9. And it was incredible. Appreciate all the hard work and thanks for the great ride with space.
Copy all.
Good luck. Proud of you and the rest of the team. Thank you so much for what you've done for us today. America back into low Earth orbit on the Florida coast.
Copy all. Good luck.
All right, so Bob and Doug in
And Dragon
space.
SpaceX confirmed nominal equals activation and service section Draco checkout. Moscone deploys in progress.
Copy all. We're monitoring.
We're here in Hawthorne, giving the crew a heads up that we have confirmation the nose cone is deploying. So again, that nose cone is going to open up a little bit more than 90 degrees, goes up 105 degrees. That's going to expose the actual docking ramp hatch that they're going to be going through once they attach to the International Space Station. Also, 4 of those Draco thrusters, we call them forward bulkhead thrusters, are going to be used for these major phase burns or firing those thrusters to actually raise their orbit gradually over the coming hours. Also heard good activation of the ECLSS, that's the Environmental Control and Life Support System, everything controlling their atmosphere, just keeping Dragon a nice, safe, habitable environment. They're going to be living the next 19 hours until they arrive at the space station.
Exactly. And Falcon 9's job may be done for today, but the mission is not over. Crew Dragon's job is not done. As you can see, Bob and Doug still inside Crew Dragon, making their way. It will be a 19-hour trip to the International Space Station before they dock tomorrow morning. And such cool views. I love that we can get these live views here and see and watch what they're doing now that they are in orbit.
It's incredible.
All right. Fun part's over. Now we get to watch them drift for the next 19 hours. So, back to where we were. So, big thing, the transistor. Transistor itself came in about 1947 as a better, smaller, cheaper, easier to make, and again, much, much smaller and more robust replacement for vacuum tubes. Excuse me. So, just like relays, just like vacuum tubes, a transistor is just a switch that is controlled by another electronic circuit. So a little bit simpler than relays because it doesn't necessarily need separate ground connections. It's just looking for voltage moving from one place and turns on a connection between 2 other points. So this pretty much revolutionized everything electronic from radios and telephone systems to making like handheld electronics and digital watches and all kinds of other stuff like that actually possible. So now that we can make our circuits a heck of a lot smaller, we can make building more complicated circuits a lot simpler too by pre-building some of our very common components. So we get into integrated circuits, 1958, which are basically transistors that perform some common function like logic gates or tiny bits of memory or counters or adding or arithmetic logic units or things that do like the math that we've been working on building circuits to do, and putting them all in a tiny little package that you can just plug into a breadboard or a circuit board or something and use out of the box, right? So you don't have to reinvent the wheel every time you want to build a circuit. Next big thing after that, little company called Intel, forked out of a company that made the original integrated circuits. So the Intel 4004, 1971, was the first thing, or one of the first things, probably the most popular of the first things that we could really call a microprocessor, like what all of our computers today use to run themselves. So this is basically that circuit that we've been putting together for the past couple of weeks in a tiny little self-contained chip. So everything but the memory, basically. Memory is a separate thing. But this has everything you need to actually process data, right? So this, along with Intel released a couple of support chips that went along with it to do like, to be a clock for actually driving the circuit to go, used other memory chips to actually store data, had some other accessory components used for like interfacing keyboards or other input and output devices. But this was really the first self-contained computer in a sense, right? Then we can actually go look at sort of the structure inside it, right? How it all works, which should look fairly familiar, kind of similar to the circuit that we've been building in a sense. So over here, this is the timing and control block, is exactly that big generic control block that I drew last week, where it's like, okay, here's the stuff that makes everything else work. We're not going to worry about how exactly it works, but that's what this thing down here is. Up here, we have the accumulator, which is that latch that was down at the bottom of our circuit that held the output of our math or whatever else was going on. This ALU right here, arithmetic logic unit, it's a word we haven't really seen, or a phrase we haven't really seen yet, but it's basically the big chunk in the middle that actually does all the math. It's our adder and the stuff to enable subtraction and some of the logic to determine how things flow through that process. Up here, we have our flag flip-flops, which we talked about yesterday, little 1-bit things to keep track of data in between different operations that the processor does. Over here, the instruction register, an instruction decoder. Again, I think in our thing that was baked into the control circuit, but this is the thing that actually looks at what is our program telling us to do, and then going and telling all of the other stuff how to do it. The stack stuff we'll talk about in a minute. And then over here, we have our registers, which I talked about last week. This is where sort of intermediate storage in between your RAM, your memory, and the processor. So all of the computations that we're actually doing right now go into the registers and then maybe eventually get dumped back into the RAM. So after the 4004, there was an Intel 8008, which was okay, but had a few issues. The Intel 8080 was the next big revision. A little bit easier to use because of, you know, the larger number of places to connect things, make it a little bit easier. You don't have to worry about using multiple pins for the same sorts of things. But this was kind of a big deal. This, along with a couple of competitors from Texas Instruments and a few other companies that don't really exist anymore, really laid the foundation for the personal computing market, as well as a lot of commercial computing stuff. If I remember correctly, the Altair that, you know, Bill Gates and Paul Allen and, you know, the Microsoft people initially got started with was based on one of these doohickeys. So chapter 19 goes into a whole lot of detail about programming and the assembly language used to program the 8080 and the Motorola 6800, which was kind of the biggest competitor to the Intel 8080. I'm not going to go dig into the details because assembly programming is gross and tedious, but I do want to hit on a couple of big important developments that sort of came along with that the book talks about a little bit. So, nope, not you. There we go. One big key thing that gets introduced here is this idea of the stack. So a stack is a fairly common data structure when you're doing programming things, and it works just like a stack of real things, right? So you have this chunk of memory, which is divided up into pieces. So I can go put something onto the stack or push something onto the stack. And it typically starts down here at the bottom, right? I can push something else onto the stack, push something else onto the stack. Then I pop something off of the stack. So I get the top thing off and it gets erased from the stack and goes somewhere else so I can use it for something, right? So this idea sort of underlays a lot of how programs that we actually write today get structured and used, right? So if we look at how the memory gets used in a modern program, we have chunks down here at the bottom and chunks that grow down from the top. So this down here, the heap, part at the top is called the stack. So as you write programs and as you call functions inside of your program, every function gets its own little chunk of memory here in the stack. So for example, if you're writing a C program, I love writing code by hand. It's the best. So if we have this simple, dumb C program, this main function gets its own little chunk of memory on the stack where all of the things that that function needs to know about get stored. So in this case, our X and Y variables here actually live somewhere in this chunk of memory up here. I'm going to call this other do something function. Which when I call it, gets put into its own, what we call a stack frame or a chunk of memory in the stack. And it gets its own copy of X and Y to play with. There is a register inside of the processor. It's called the stack pointer. I'm going to call it SP for now. And it points to the place in the stack where everything, all of the code that is running right now should be looking at. So while we're inside do something, the stack pointer is pointing at this chunk of memory right here. After do something is done, there's another mechanism I'll talk about here in a second that changes the stack pointer to point back to our original main function, right? And then the heap down here holds all of your dynamically allocated stuff. So if you're talking about C++, all of your objects, generally speaking, get thrown onto the heap. Anything that you allocate, not just declaring variables, but allocate later, that all goes and lives on the heap. Anyway, so that's the idea of the stack. The other thing that gets talked about in here that doesn't get talked about, or that we haven't talked about before, that is super critical to how programming works today, is the idea of the conditional jump. So last week we saw, actually, no, I'm not going to put that in. So last week in our very simple program, I'm going to not, I don't want to start there. Actually, that's not, that should be. Okay, so very simple program, kind of like what we saw last week, where I'm going to load my data from memory location 0. I'm going to into the accumulator. I'm going to add whatever's in memory location 1 and add whatever's in memory location 2, and then write the results of whatever this addition is into memory location 10. And then, just for the heck of it, and we will, oops, I started too far on that side. So this is memory location, this 101, right? So this program right here is just going to do this simple addition problem over and over and over again, right? I'm going to load a number into memory. I'm going to add another number, take the results of that addition and put it somewhere else in memory, and then jump back to the beginning and do this over and over and over and over and over again, which not super useful, right? So pretty sure this came in with 4004, but it introduced the idea of a conditional jump. So, for example, jump only if the carry bit or the carry flag is set, right? So we're only going to do this jump if our addition problem here set the carry flag, right? So if we go through and all of these numbers are relatively small, then we're just going to keep going. Our program's going to keep running to whatever comes next, right? But if we add these numbers up and they are bigger than our accumulator can hold, and the carry bit gets set, then actually I said that exactly backwards, but we'll just fix that. Okay. So if we're only jumping if the carry bit is not set, when these are small, then this will not jump because the carry bit's not set and keep going. If these are big and the carry bit does get set, then, crap, I just said it backwards again because I changed what I said. Ha. This is what I get for not running through these exercises beforehand. So we're going to go back to the original plan. Jumping if the carry bit is set. So if these are small, then when we get here, the carry bit is not set. So because it's not set, the program's just going to keep going onto whatever comes next. If these are big enough to set the carry flag, then when we get here, then the carry flag set and we're going to jump back to the beginning. There's lots and lots and lots of different things that we can check for here, not just whether the carry flag is set, but whether, one register, the contents of one register are bigger than another one, or rather the contents of this register is 0 or not, or all kinds of other different comparisons that we can use to jump around inside of our code, right? So this basically lets us write programs that can do a lot more complicated things. So we're not just going through step by step and doing stuff in a very linear fashion. We can now jump around. We can reorganize our code into reusable bits of pieces and functions and stuff like that, so that our code is a little bit easier to read. We can make our computers make decisions for themselves. So I'm not necessarily just telling you exactly what to do. The computer can make decisions based on what else is going on inside of it, right? So that really means that computers can start doing much more complicated tasks, which we have definitely taken advantage of. Is there anything? No. Yes. So one other somewhat important thing that gets mentioned in chapter 19, the idea of a 4-bit or 8-bit or 16 or 32-bit processor. So the computer that we've been building, the circuity thing that we worked on last week, is an 8-bit computer because most everything inside it is based around 8 bits. The data transmission is 8 bits. The amount of memory, or the size of the stuff that we get out of memory at a time, is all 8 bits. Our adder works on 8 bits at a time. So it is an 8-bit computer, right? The Intel 4004 was a 4-bit computer because everything inside of it was 4 bits wide. Most computers that we have sitting on our desks or sitting on our laps or even in our pockets today are all 64-bit machines. Everything they do is based on 64-bit wide data. So that's a kind of an important concept to know. It also talks about how everything that, one of these 4-bit computers can do, or to put it another way, everything that one of our modern 64-bit computers can do is basically doable on one of these 50-year-old 4-bit machines. It's just going to take a lot longer because it can only work on data in much smaller chunks at once. So, pretty cool concept. Okay, so I believe that is it for this week. Any questions, comments, concerns? I take that as a no. Oh. Is that a yes? Do I see movement?
I was just going to say that the Shannon
Claude
guy.
Shannon. Yep.
Yeah.
Yep.
Computing and cycling while juggling. I couldn't tell if I was in his office or not. But other than that, no questions.
Cool. All right. So next week will be the end of our little tour. I'm just going to do a very quick overview of the last couple chapters of the book, and then we'll call it good, and then maybe move on to a different book after that. So I will see you all next week.